Okay. I was like,
Guys were wearing coats.
this?
Yeah.
Is that the goofy hat?
Yeah, it's a Windows HPC Server 2008.
Bench. Something
Awesome.
interesting.
Okay. Yeah, I don't think I'd wear that hat. I need hats, too. Okay, so any comments on Matt's talk?
I wish I spent more time on the last part.
Okay.
Yeah.
Sorry, the which part?
The part where he was talking about the new algorithms of the pipeline.
Yeah, I mean, I think part of the issue is, it's a little bit secret. I mean, they don't really want to talk about that in too much detail. But two is it's just not really fully baked yet. I mean, I think this is the most important research problem in graphics, I think, in the next 5 to 10 years. What kind of new pipelines can you do when you free yourself from the traditional graphics pipeline? I don't think anybody has really good answers for that. I mean, one thing we're going to talk about next week, sort of my talk on Tuesday, is Raise, which is the pipeline that Pixar uses. And so there's a lot of interest in being able to do Raise-like functionality. But even that's just taking a pipeline that hasn't been done in hardware and putting it into hardware. I mean, I think the real thing is going to be what new pipelines can you think up that nobody's done before? So but I don't think he has all these answers for that. I think they're concentrating on just building really good renderers today to do more traditional kinds of things, and then hopefully developers will think up cool stuff.
Something I thought about, I wish I thought of it when I was talking, was how much of it will be open source. I mean, if it's a very fast pipeline done that's going to run all of the graphics that we know now.
Yeah, so the trade-off there is, I mean, so they sort of have I think he talked about Michael Abrash a little bit. He's sort of writing the low-level render. Pixar bought a company called, I don't know, the product was called Pixomatic. And so it's a software rendering pipeline that developers used. And so the low-level Larrabee pipelines are based, partially on that. And so I don't know if they're going to release that. Then the higher level renderer stuff is stuff where they would probably be more likely to do that. The issue is, I think, so when you come up with benchmarks, you really want to do better than the other guy at the benchmarks. And so if you know everything the other guy's doing and you know the algorithms they're using, you can probably make up a benchmark that makes them look bad. So if you don't release that stuff, nobody will see what sort of the holes are in your implementation, because absolutely NVIDIA and AMD are going to be looking at whatever things Larrabee comes out with and trying to figure out what they can do better than Larrabee. And Larrabee's going to do the same thing to HP and to NVIDIA and AMD. So the less you release, the harder it is to do that reverse engineering.
I have a question regarding the cell processor.
Yeah.
Obviously Sony, and they have probably a similar API that they need for their, for the cell as well. I mean, they need an OpenGL-like. API on top of the cell.
So for doing PlayStation 3?
Well, back to, say, Larrabee versus the cell. I mean,
Okay.
It seems as if the architectures are similar in that they, besides maybe some of the memory and the cell has the DMA, whereas maybe there's some sharing available with.
Well, the deal isn't something like the PS3, which has high-performance graphics. The graphics are being done by an NVIDIA
Another
chip.
graphics card, right?
So I don't know that that IBM has this awesome full software renderer all in cell. Like if anybody's built like this awesome cell rasterizer, for instance, I don't know about it.
So I was talking to Pat Hanrahan about this. I was working with the Tungsten Graphics guys on an open source OpenGL driver for the cell.
Okay.
And Pat's comment was that that they looked at this a couple of years ago, and that the memory bandwidth on the cell just wasn't good enough to support what was needed for like texture fragment operations.
So my understanding of the original PS3 design was that they wanted to do it with like basically 2 cells. And then they said, okay, we're going to do it with like 1.5 cells, and we're going to take the other half of the cell and put in fixed functionality to do texture filtering and rasterization and so on. And eventually they ended up canning that whole thing and saying, okay, we're just going to buy an NVIDIA chip, and that was sort of a last-minute decision. I think it would be difficult to do an architecture that wasn't designed for graphics, that was general purpose, and be able to get competitive performance. The only way Larrabee succeeds is if the things that are hard to do in special purpose things are things that they designed for. So putting in fixed function texture functionality, or building an instruction set so that rasterizer is really optimized. That's hard. I mean, they've done a lot of work to the architecture to make it well suited for doing software rasterization. Cell didn't do any of that stuff. Cell just has a vector architecture. So. I think in general, if you're going to use the cell to do high-performance stuff, basically the cell can be, the vision in the PlayStation was the cell was basically the vertex processor. It would do great floating point performance and then send everything down to the graphics card to do the rest.
That's one thing about the Larrabee talk, which is he kept saying that, there's all these programmable stuff and everything's programmable. But then he never really mentioned this one big killer app that NVIDIA and that just cripples NVIDIA or AMD chips. And then at the end he just says we'll let people figure out what this app will be at the end. And isn't that such a huge gamble for Intel?
Yeah, it is, and it's. But I think history has shown that when you give people programmability, not only in the graphics pipeline, not only do they use it in sort of the ways that you intended, but they use it in ways that you haven't intended to. So I think it's a good gamble to make, to say if we give developers this functionality, then we're fairly confident they're going to be able to do neat stuff with it. Yeah, no, I think that's accurate. The trend has been toward more programmability. People are doing cool stuff with it, and if that's the case, then I think I'm sure people are going to use it in some really interesting ways. So our guest on Thursday is going to be Bill Mark. He is, he's come from, he was at the University of Texas, where he was faculty before this. He was a postdoc at Stanford. He was the lead designer of the CG language at NVIDIA. So if you used CG, which is one of the first shading languages, he was the chief architect of that. He did his PhD at North Carolina. He now runs Intel's graphics research group. And the talk that he's going to be giving is, at least the way it was explained to me, is at Intel they have lots of amazing CPU designers. And they want to teach the people who know graphics aren't very many. And so the people that really know graphics are trying to teach CPU designers how to design GPUs. So basically, what's different about the GPU? What do you need to know if you've only designed CPUs and you want to design a GPU? So it's a great lesson within Intel, but it's also a great lesson for us because most people have more experience. When we teach classes here, you learn how to build CPUs. So anyway, he's a really good speaker, really bright guy, and I'm definitely looking forward to having him out. Okay, anything else before we get started on today's topic?
Any idea when Larrabee comes to market?
I think you can go to Wikipedia or something, or I guess the Inquirer will probably guess. I think the current target is first half of 2010. So sometime now plus a year, plus or minus 3 or 4 months. Yeah.
They will keep continuing a new Larrabee architecture every year, just like the other ones?
I think, they're not going to stop at one. So Intel tends to have longer design cycles than NVIDIA. So surely they're already. The other thing that they do differently is because they own their own fabs, they build silicon early and often. So they would get back. It's entirely possible they already have silicon back in the labs, and they're learning. They basically debug hardware. So that's a little of a side then. So they debug hardware, find out what went wrong, and then they do another spin of the silicon. Because they own the fab, they can do that. Something like NVIDIA, that's very difficult to do because NVIDIA doesn't have its own fabs, and it's really hard to get fab time. It's very expensive. But Intel can get away with that. Will, does that match your experience? Okay. So if you're NVIDIA, then what you have to do, since you can't build silicon but you need to test, is you buy these enormously large FPGA machines from companies like QuickTurn. So it's basically like 2 refrigerators full of FPGAs. And you map your entire design on them. They're really expensive. They're tens of millions of dollars to buy one of these machines. And then you can run things at 2 frames a second. Okay? But you can actually test it. You can boot up your silicon. So the rumor is with Larrabee that when they bring back the first silicon they get, they will run more Larrabee cycles in the first second when they turn on the Larrabee than have ever been run before in simulation. That's like the speed gap between what you can do in simulation and what you can do with real hardware. At least simulation at the lowest level when you're actually doing gate level design. So just a different focus there in terms of how they spend their resources. Okay, what we're talking about today is sort of the last half of the graphics pipeline, composition to display. What I'm going to do next Tuesday is we will talk about juggling the pipeline. So sort of, if we start looking at things like, hey, you'd like to be able to put this new stage in the pipeline, or you'd like to be able to juggle it around, we will definitely look at Raise, which is the Pixar's architecture, and sort of talk about that. And when Jeremy comes next week to give a talk, that will certainly be relevant. But I'll talk about some other cool stuff that's been done as well, because there's definitely been some interesting research in that area. And hopefully it'll get us thinking about, okay, what could we do with a more programmable pipeline? Jeremy will come a week from Thursday, and then the next Tuesday I will talk about parallelism in graphics. And we'll, one word you heard from Matt was this idea of sort middle. He said, oh, we have this sort middle architecture, and you probably all are scratching your head. So we'll talk about sort of classifying parallel rendering approaches and learn about things like sort middle. And that's been left to the last lecture. And then that Thursday, you guys are going to give your talks on your projects. Okay, so 4 things we're going to talk about today. Anti-aliasing, compositing, depth buffer, and monitors. And so we're going to start off just by thinking about what a pixel is. And so I mentioned last time Alvy Ray Smith wrote an article on this. It's a very interesting name for this particular article, but he wanted to make sure that you understood that a pixel is not a little square. So you can go download this, get cited, and so on. So what a pixel really is a point sample. It's a discrete point. It's not an area. And what an image is a grid of point samples. And so an image is a discrete thing. Okay, it's a discrete grid of point samples. And if we want to say, okay, what's the function over that image? What's the continuous function over the image? Then that's something we can do mathematically with the sampling theorem. And so the sampling theorem basically says if you have all these point samples in a regular grid or regular line, and you want to reconstruct them into a continuous function, there is a fixed way to do it. It's a way it uses sinks. If you've done any signal processing, we'll see those in a minute. And there is one right way to reconstruct that theorem. Okay? And your eye also does this too. All right? Your eye has a certain number of receptors. We'll actually see this a little later in the lecture as well. And so your eye is basically doing a lot of sampling. But we as people think of it as a continuous image. We don't see a bunch of points. We reconstruct it in our brains to be a continuous image. So what does a pixel do? What it represents is it looks at a particular area of things. So basically, to get a pixel, you want to integrate over this particular area. And if we do point sampling, just like we did in texturing, then we approximate that area with a single point. So what we really want to do, though, is to be able to take this area that the pixel is covering and to integrate over that whole area and get back one color. Okay, to get one color out of that. And it's hard when you start having all these different things that go back, wrong way. Okay, lots of different polygons, lots of different shapes covering this area. Okay, some of them are transparent, some of them are not. Okay, our job is to integrate over all those and get one color out of it that we're then going to display. All right? So what's the filter function look like? Well, you might say that if we sort of looked at a pixel as this little square kind of thing, and we have a lot of little squares around here, okay, then maybe our function, is pretty small here, and it's like some sort of, Gaussian kind of function, depending on the kind of display that you have. A signal might bleed over into other pixels and so on. You might prioritize the center of the pixel as opposed to the outside, and so on. So there is a filtering function for a pixel, and it depends on the properties of your displays. So what we want to do, the right way to do this, is you render all this geometry of this big list of geometry at every pixel, then you sort of smash it all together into this big integral and get back some sort of color. So basically what we're talking about in the first part of this lecture is how do we fake that best we can, because that's a pretty complicated process. Okay. The other question we have is we're going to try to do this in such a way that we don't alias. Okay? And so this is sort of our jaggy kind of thing. And we're going to the way we're going to try to do this is we're going to say, well, what we're trying to do is this line here, but we don't have the precision to be able to do that. So we're going to try to get a better approximation for shapes by taking more samples. Okay? If we take more samples, that's going to raise the Nyquist limit. We're going to be able to represent a better approximation of the actual shape of this thing. Okay? We're only sampling on a discrete grid, but the higher frequency grid we can make it, maybe that's going to alleviate some of our problems. So the things we want to think about as we're looking at different ways to anti-alias are these. Right? How much more does it cost in terms of hardware? Okay? What's the impact on the programmer? Does the programmer have to change the way the programmer is actually writing code to use these anti-aliasing methods? How do we control sample locations? All right? We're going to take samples out of our shapes to figure out where we're going to sample. Do we get to control those? And what people really notice is, as we do anti-aliasing, how does it behave with horizontal and vertical lines? So what I mean, well, we'll see what I mean here, but it's something you want to think about because that's very jarring to our visual system. Okay. So our simplest thing that we're going to do is what we call supersampling. Okay? Basically, we have a screen that's 1,000 by 1,000. We want to do a better job of representing our final image. So what we're going to do is we're going to render the whole scene at 2,000 by 2,000, and then we're going to downsample. Okay? We're going to take 4 points and combine them into one. Okay? That's good because we've essentially rendered the scene at 2,000 by 2,000. Maybe we'll have a better chance here and say, well, this pixel, it barely misses the sample point there, so we would color it white. But if we take more samples per pixel, then we can say, well, 2 samples are covered and 2 samples are not covered. So we'll render this as half green instead of full green or white. Okay? We're basically trying to take an area integral here. We're now taking more samples, and that can hopefully give us a better approximation of what the actual value of this should be. Okay, so really simple process to think about doing. So what's the hardware cost here? The hardware cost is that you need a buffer that's bigger. If you do n by m samples at every pixel, you need a bigger color buffer. So this is called full screen anti-aliasing. If you look at all the graphics, if they're trying to sell you a graphics card, they're going to say, oh, my graphics card supports full screen anti-aliasing, and that's what they mean by this. Usually we're going to say it's n by m. Okay? That means we're going to take n samples by m samples. So down at the bottom right there, that would be a 4x4 super sampled image. Okay, so does this work? Okay, so this is out of a image processing kind of textbook, and we're moving from single point per sample to more to more to more. Okay, and one thing you can see up here is an amazing amount of aliasing there. Okay, it's because, again, the Nyquist limit is low, and so up at the top you're going to see high frequencies masquerading as low frequencies. As you take more and more samples, the image gets better and better because we're doing a better job of, we basically raise the Nyquist limit by taking more frequent samples. Okay, and this is, looks pretty solid over here. Here's a graphics picture. So this is 1 sample per pixel, 2 samples per pixel, 4 samples per pixel. All right, so what looks different here? Okay, so this is usually the place where you're going to see this the most are things like silhouettes. Okay, so if you look at you got jaggies on the arms here as you walk down the arms. If you look over there, it looks much, much smoother. Okay? And you're going to see these sort of effects mostly at discontinuities. So if we got a discontinuity between the arm and the background like we do here, okay, that's discontinuous. If we're taking multiple samples, then basically we're blending better between the arm and the background. And that makes sense because we're essentially trying to take this area integral over something here. If we only take a single sample, we're going to do a bad job of approximating that integral. Yeah. Okay, so this is kind of an old picture, but hopefully it's showing it pretty well. But yeah, silhouettes are something that definitely looks better if you take more samples. Okay, so we take a bunch of samples. Okay, what do we want to do here? Like, how do we calculate the color from all these samples? All right, so the way we're going to do that is we're going to have a whole bunch of samples. Okay, that's the C in the equation, and then weights per sample. All right, and then all we're going to do is add them all up. Okay, so that's pretty simple. So what are the weights going to be? It depends on the filter that you use. If you use a box filter, for instance, if you're saying everything in the pixel counts the same, everything outside of the pixel doesn't count at all, then you're probably going to have the same weight for every pixel there. But if you have something that looks a little bit more like a Gaussian here, and you count more of the ones in the middle of the pixel than on the outside, then you're going to have a different set of weights. Okay? So one of the goals here is that in developing a filtering scheme is you would like each sample to contribute the same amount to the image. And the reason we want to do that is because you're going to the same amount of work to produce every sample that you take, right? You're going to have to rasterize it, you're going to have to shade it, and so on. So if it turns out you do that, and then you're this second-class sample, and they don't use you very much in the image, then you've gone to a lot of work for not very much good. In theory, any sample you take across the whole image ought to have equal importance. And so just the filtering schemes we're going to look at are ones where all the samples do have the same weight, and we'll see how that ends up working. Okay, so box filter basically says, okay, if we want to properly reconstruct this, okay, then we're going to take only these with the same weight and take everything out, right? So this is a pixel here, this is a pixel here, and this is a pixel here. So this is a very simple thing to do, and the weights in the box are the same for every sample that we take. Okay, you could say, all right, we're going to count the ones in the middle a little bit more, and then these things are going to overlap, right? So you'd have another triangle here and another triangle here, and so on. If you do that, then all the weights are going to be the pixel is going to contribute the same amount to the image no matter where it is. The sample will, sorry. Because if you're here, then you're only contributing to this pixel and not to these. If you're halfway between two pixels, then you contribute half to this guy and half to this guy. So you'll contribute the same amount of paint to the final image. The right way to do this is a sync filter. And so this is some signal processing mumbo jumbo you don't really have to worry about. If you want to do proper reconstruction using Shannon's theorem, then the right filter to use is the sync filter. So it's got a couple of problems that make that a little more difficult. The first are these negative lobes. Okay? If you have paint in here, then you're actually taking away paint from the final image. Okay? You have a negative contribution. The second thing is the sync filter extends forever. So it's pretty hard, basically a pixel contributes to the entire image. And if you're trying to calculate one pixel, you have to consider every sample in the whole image. Maybe not the most convenient thing to be able to do. Okay, so pretty much in practice, you're going to do something that's a little bit, let's see, more practical than the sync filter, right? So if you're using a box filter here, okay, and you reconstruct an image from samples, okay, then you're going to get a function that looks like this, right? So it's sort of a boxy kind of function. Okay, it doesn't look very contiguous. If you do a tent filter, then you're going to get one that's piecewise continuous, so it's C0 continuous but not C1 continuous. If you do a sync filter, then you're going to get the right answer. Okay, a sync filter will allow you to take discrete samples on a grid and be able to come up with a band-limited function that's the right representation of this particular function. Okay, so in practice, the box filter is pretty much the one that people use in general. I mean, if you take one sample per pixel, this is what you're going to use. If you do supersampling, you're essentially also just doing a box filter. But if you look at, like, say, what Pixar does in their movies, they're going to do post-processing that does some, much nicer filters that match very nicely what their camera looks like.
Are each of those impulses subpixel? Sampling. I'm trying to figure out what the impulses mean.
Right. So these are just samples on some sort of grid. It's probably easiest to think of these as a sample of one sample per pixel. Okay. If you do supersampling, then what you should do is, let's say you do 2x2 supersampling. You take those four, you average them together, and then they become this sample per grid, because that's what in practice really happens. Okay. So, all right. So. I'm not really worried so much about the signal processing kind of stuff, but you should know that the box filter is not a very good approximation of the final signal, but the more effort you put in, the better approximation you can get of the continuous signal that's presumably the original signal. Okay, so supersampling is really a brute force approach. You basically have to render the scene at a higher resolution. Okay, and that's expensive, right? That's the most expensive thing that you can do. So people have tried to sort of cut some corners and say, all right, supersampling is too expensive. We don't want to double or quadruple the cost of rendering our scene. Instead, what we're going to do is we're going to multisample. We're going to take multiple samples per, but we're going to cut some corners. We're not going to do full everything. So the first thing we do is we figure out, okay, what are the multiple sample points we'd like to take per pixel? So this is kind of an important point, right? You're going to have a pattern on every pixel, and you're going to take certain samples of that pixel, just like we did in the supersampling case. Okay? It's okay if you have a different pattern on different pixels. Okay, you can have this pattern on this pixel, different pattern on a different pixel. That's cool. You can deal with that. What you can't do is have the pattern differ with time. You can't have it having one pattern at one frame and then a different pattern on the next frame. And the reason is because that's really visually disconcerting. If you were watching this thing and it's taking different samples here and the colors are changing even though the camera is not, you would find that very, very distracting. So that's bad. Okay, so here's what we're going to have per fragment. All right? A fragment is going to have, it's going to say which samples it covers, okay? So, and a color and a depth and a texture at each one of those fragments, right? So this is where the word fragment actually came from. You're sort of covering a piece of a pixel, right? You're covering certain samples. You're keeping track of which samples you cover and which samples you don't cover, and then you compute color, depth, and texture coordinates. Now, this is cheaper than supersampling because of this line. Okay? So the real expensive thing in rendering is often doing the texture lookups. You have to do a lot of texture lookups. You're not going to do one texture lookup for every sample. Okay? Instead, you're going to do one texture lookup for the pixel, and you're going to use it in each one of these samples. And then you store all these different samples, all these different samples in this big linked list, and then you have this linked list of samples, and you have to squash them together somehow to make a final pixel value.
So in this strategy, we're not, you said that we're not going to do a texture lookup for each of the fragments as we sample.
Right.
But instead we're going to compute an average of color, depth, so on and so forth, and an average of the texture coordinates, and then do a lookup there. That seems really weird. I mean, I understand why you would want to do it that way, but it seems like it's going to give the wrong answer.
Well, I mean, using board. The thing that it does well in, okay, is let's say we've got 4 points here, okay, and we have this triangle and we have this triangle, okay. This strategy is really good for that because it means that you're going to have one fragment that is this side here, and you're going to have a different fragment that's this side here. It's probably more important that you have sort of the pixel coverage information. You say this guy's covering half and this guy's covering half, than it is for you to compute different texture coordinates here and shade these differently. Like these two things, if this is the woman's arm and this is the background, differ way more than these two things would. So it's nice to be able to basically have sub-pixel resolution as far as what you're covering. Does that make sense? What seems weird about this to you?
Well, so we're not having to interpolate space.
Right, so the question is, do these two things basically don't differ? You shade once. You shade once per fragment as opposed to once per sample.
Yeah, I'm sorry, that didn't come out right. So we're not having to interpolate. So we're sampling within an area, summing up, color. And so at the end of that, we get a color for this entire thing. Now, so if we sample the texture for each of these samples and average them together, we're going to get one thing. If we then average the texture coordinates together and then do a texture lookup, we could conceivably get something different.
Yep. It's, well, you can pay the cost and do each of these samples separately and compute a different color for every sample and then just sort of squash them all together, right? That's full screen anti-aliasing. That's the supersampling technique. The question is, how can we cut corners and pay less of a cost? And instead of doing one texture lookup per sample, we will do one texture lookup per fragment. Okay? That saves you a lot. I mean, because if you have lots of samples in here, you're potentially saving, if you have n samples, you're saving n to 1 in terms of texture bandwidth. So that's a big win But you still get the benefit of having multiple samples in here to resolve visibility.
Are there any papers comparing the visual quality of one to the other? It just makes me really nervous for some reason.
No, it's a spectrum, right? From point sampling to multi-sampling to supersampling. Okay, probably. I'd say it's probably more of a vendor sort of thing. Okay, in general, the vendors will offer multiple of these. They'll have multiple anti-aliasing modes, and you can choose between them. Okay, so the next question we have is, well, where do we sample? All right, so we saw in the full screen anti-aliasing case, one way we can do it is we can just have a regular grid. All right, so you can either take a bunch of random or pseudo-random points, okay, and that will give you better filtering. It basically gives you better performance. Or you can do some sort of regular grid pattern. And it turns out that's a lot easier to sample, right? If you sample on a regular grid, it's a pretty easy thing to be able to do. But it's not going to look as good. So the compromise pattern that people do is they have a regular grid, and they only take a certain number of samples out of that. Right? So here we've got 64 points over here, but we're only going to sample from 8 of those points. Okay? And that's, it turns out, I mean, we'll look at some psychophysics kind of stuff soon to see, that that's really the right thing to do. To do basically some sort of random-ish kind of sampling is a better thing from a signal processing point of view than to do a regular grid. And the thing that's really bad with a regular grid, okay, is horizontal and vertical lines. Okay, and we'll come back to the other one in a second. Okay, what you want is the ability to, all right, let's go back here. Okay, this is an entire pixel here with a bunch of samples on it. All right, and I'm drawing a line and it's creeping up. Okay, the bad patterns are ones where there's a big jump in the color because okay, try this one over here. Let's say I did 4 samples and they all looked like this. Okay, these are my 4 samples. All right, and I'm drawing a line here, and there's like a plane under here, and this is white and everything else is black. And I'm drawing here, drawing here, drawing here. It's white, 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 black. Right? You have all these extra samples, but it turns out they're not doing you any good because they all sort of turn on or off at the same time. Okay? You don't like that. And it's especially jarring to us visually when that happens with horizontal and vertical lines. That when you have, there are more horizontal and vertical lines than other kinds of lines, and as these lines move, if you have this sudden jump in intensity because you just turned on or off a whole bunch of samples at the same time, that's bad. You want to avoid that. So look how nicely this works here, right? As you go up, it's sort of gradually 1/8, 2/8, 3/8, and so on. And the same thing here, right? As we go across, 1 turns on, 2 turns on, 3 turns on, 4 turns on. When you resolve all these samples together, you're going to have this nice, smooth little blend as you move across. So that's a really good thing. So the kind of patterns that you want, the pattern you really want here is it's the 8 queens pattern. So you want to be able to put 8 queens on the checkerboard here and have none of them check each other. Okay? This is not the 8 queens pattern. Right? What's the kind of line that doesn't look good with this sample pattern? Right, so if I go diagonally here, it goes 0, 0, 0, 0, 3, 7, 8. Right, so that's not so good. This is not a very good sampling pattern. Okay, it's better than some other ones we could pick, but it's not as good as we could. So an 8 queens kind of pattern is a good thing to be able to have.
I mean, isn't that really easy to do, though? I mean,
pardon?
Isn't that really easy just to make one template of an 8 queens pattern?
Yeah, you totally can.
I was just wondering why.
I'm only using it to show that some patterns are bad. Okay, so this is sort of a visualization of that. As your line goes up, you hit one, then you hit the next one here, then you hit the next one here, and so on. Right? You have this gradual from 0 to red. So this is a particular scheme called rotated grid supersampling. And so you sort of have a nice grid, and then you turn it by a few degrees. And so that gives you pretty good behavior. So this is a nice grid to use if you're doing 4 samples per pixel. All right? So it works very nicely for horizontal and vertical kind of edges, which is groovy. NVIDIA has one called the quincunx pattern, which is the weirdest name they picked. So what a quincunx is if you look at a die, like the kind you roll, okay, you roll the dice, the pattern 5, okay, sort of 1, 2, 3, 4, 5. That is called a quincunx. Okay, great Scrabble word. Gets you lots of points. Okay, so this is kind of cool because this is the particular. So this is one of their schemes that they used. They took samples in the middle, and then they took samples at each corner. All right, so this guy would count for half when they did their weighting, so it's sort of this Gaussian kind of thing here. And these guys would count for an eighth each. Okay, but wait, we said, we want all the points to count the same amount. And so this guy counts for an eighth for this guy, but he also counts an eighth here, an eighth here, and an eighth here. And if you add those up, he counts a half. And he counts a half also. So every pixel, every sample you take ends up contributing the same amount to the final image. Okay? So this is cheaper than rotated grid supersampling because you're only taking 2 samples per pixel. Right? He's taking, this sample has, this pixel has these 2 samples, this pixel has these 2 samples, and so on. Okay? So cheaper, and so they'll have some nice marketing diagrams as far as, how this ends up looking. Tomas did a paper called Flip Quad. And so they said, okay, 4 is too much. We don't want to do 4 samples per pixel. Instead, we're going to do 2 samples per pixel. And the way we're going to do that is we're going to slide the pixels out to the outside. And then they're going to share. So every sample we take is shared by 2 adjacent pixels. So this one's a little bit interesting because you have 2 different patterns here. So remember we said it's okay if patterns differ spatially, but it's not okay if they differ temporally. So I actually reviewed this paper when it was under review, and one of the big questions was, well, does it matter if they differ spatially or not? Like all the reviewers were arguing about this. We decided eventually it was okay. So thumbs up there. So when I assigned, homework 2 is investigate something in the graphics pipeline that isn't told. And so 2 years ago, a couple students looked at this, and they looked at what the sampling patterns actually were. Okay, so where are the samples actually taken within a pixel? So you could do experiments to figure that out. Right? You draw these little tiny pixels all over, little tiny squares, and you figure out what turns them on and what doesn't turn them on. So this picture is probably a little easier to see. If we have, what they found was there is a grid in here. Okay, so there's sample positions only at certain places in the grid. Makes sense. And if we take 1 sample on this particular ATI hardware, that's where it is. 2 samples is this pattern. 4 is this pattern. And 6 is this pattern, which is kind of a weird pattern. But both students that did it ended up with kind of the same shape. Right? So this is a different student that did the same experiment, and the red ones were the ones that belonged to that particular pixel. So it's kind of a neat outcome. So how do people actually sample? Well, they had 4 different anti-aliasing modes, and these are where the samples were for each of those anti-aliasing modes. Okay, so anybody have any questions about all these different ways to sample? All right, so there's other ways we could try to do a better job of anti-aliasing. One of the ways that SGI hardware did for a long time was called the accumulation buffer. This is pretty cool stuff. So what they do is they have a buffer, and graphics hardware has this today too, this accumulation buffer. So it's like a color buffer, but it has more bits of resolution. Right? So instead of just keeping 8 bits per pixel, maybe you keep 12 bits per pixel. So high-end SGI hardware had this in hardware. So here's the way we're going to do it. We're going to render the scene, and then we're going to move the camera just a little bit and render it again. And move the camera a little bit and render it again. Move the camera a little bit and render it again. And we're going to take all the results and we're going to accumulate them in the accumulation buffer. Okay? And this will allow you to have motion blur or depth of field. So you can either slide in space a little bit, or you can slide in time a little bit. Okay? So one will give you depth of field, one will give you motion blur. And so things that don't move maybe come out nice and sharp. Things that do move, you can get a nice sort of smooth blend. So this looks a little funny in terms of an image, right? You look at that and you say that doesn't look very good. This is the way that you want to do it if you're actually showing a movie. If you're showing moving pictures, individual frames look like they have blur like this. This is actually the right thing to do. What you're essentially doing is integrating over time. Okay? Over this time stripe, this 30th of a second, what light actually comes in the camera? Well, it's going to be smeared like this if you actually take a picture. So the good thing is, the quality goes up as you spend more time. It's real easy to use. You can sample any way you want. The disadvantage of this, and where people are really trying to move, is when you do these techniques, you really want to shade only once per pixel. Okay? Shading is becoming the dominant cost in real-time graphics. It is absolutely the dominant cost in offline graphics. Okay? To compute the color is the most expensive thing. And when you render the scene here 8 times, you have to calculate every pixel, every fragment 8 times. Okay? You don't like to be able to do that. So one thing we'll look at next week when we look at Raise is designed around the idea that you only want to shade everything once. Even if you're going to use it multiple times, you only want to pay the shading cost once. And the whole pipeline is designed around that idea. Okay, so kind of the right thing to do here is a data structure called an A buffer. So what we want to do is we want to take all of our fragments that are associated with a given pixel, and we're going to keep them all around. Okay, so we have this big grid here, and at this particular pixel, maybe we rendered 14 different polygons. So we want at this pixel a big linked list data structure that contains those polygons. And then once we're done rendering the whole scene, at every pixel, we're going to have this list of fragments. Okay? And we want to resolve all those fragments into a final color. So every pixel, we're going to store depth of the final pixel and this list of fragments. And every fragment is going to say, what part is it going to cover? What color is it? What's the farthest depth and the minimum depth? Is it transparent? And so on. Okay, so after you render everything, you have this giant list of pixels, of fragments, and then you resolve them all in the final step. Okay, this is something nobody's built in hardware yet, right? The real hard part in hardware here is that you can potentially have, an infinite number of fragments at any given pixel, right? You could render, 10,000 polygons, all of which are partially transparent, all of the same pixel, and you have to have a data structure that's going to support 10,000 fragments of that particular pixel.
Do you remember the Stellar GS1000?
I do not know that machine.
Yeah. Circa 1988, 4 processors, each one with a vector unit, has graphics hardware. It did hardware, spheres, and hardware sorted transparency.
Okay.
Yeah. Craig Epson and Keeler did the V-buffer paper and volume rendering like 88, and I think they implemented a V-buffer with variations in hardware. It's very cool.
So then he went to SGI later. Okay, so let's see. I couldn't drive yet, so I wasn't really looking at I don't know anything that happened at that point. So what the difficulty is doing an arbitrary amount of storage. So you could totally build this if you said, all right, every fragment could have, every pixel could have up to 4 fragments or 8 fragments. You could build enough storage for that. The problem is coping with the really bad cases. So it's something that CPUs are pretty good at, right? You can just keep allocating memory or so on. Maybe you have the size of your virtual memory space. It's a hard thing to do anything where you say arbitrary size in hardware. So I don't know this work, but my guess is it probably had a limit in terms of the number of fragments that you could actually handle per pixel. So, but this is the sort of thing that Larrabee would be really neat to do, right? You could implement this in software if you needed to. Okay, it's easier to implement it in software than it is in hardware. And maybe they're going to be able to do, a good job of doing an A buffer kind of thing. And that's potentially something we can ask Bill when he's here on Thursday. So this is what's actually used in RenderMan. So RenderMan keeps track of this. So it's good because, it really works. It's a good thing to do. It does transparency correctly. It's easy to program. You just stack all these things up, and then the system takes care of combining them all. One of the nice parts is that if you have a simple case, if you do rasterization, it only covers one thing. Like you're rasterizing my shirt here, that's the only thing we're drawing. It's only going to generate one fragment. Any fragments behind me are never, they're going to fail the depth test. So there's no penalty for the simple case. Okay? Unlike in supersampling where we take 4 things right here. Okay, so that's a good thing. The problem is it's hard. So this is it's hard to build, and it's definitely hard to build in hardware. Okay, so go over a little more sampling theory. We talked about the top part already. We talked about the Nyquist limit when we talked about texture stuff, and the nice part about supersampling is it raises the Nyquist limit. We can now represent higher frequencies than we did before. Okay, so if we reconstruct a continuous signal using the sampling theorem, okay, the sampling theorem says I will reconstruct this signal, and I can promise you that it's only going to have frequencies under the Nyquist limit. If you do that, there's only one way to do it. Right? It has no ability to generate anything that's above the Nyquist limit. Okay? There are rules to regenerate the signal, but it's not going to generate any frequencies that are above the Nyquist limit. So, if you do have frequency components in the original signal that are above the Nyquist limit, if you reconstruct using the sampling theorem, they're going to alias. And that's bad. We don't want aliasing. Okay? Aliasing is really what we want to avoid. So, the right way to do sampling is what we call stochastic sampling. All right? So this is a paper by Rob Cook. He's currently vice president at Pixar. Really, really bright guy. So here's the way that we're going to want to do it. So Wolberg, who wrote the image processing text, a very good text, he said, the ideal sampling pattern is this broad, noisy spectrum with minimum low frequency energy. All right? The problem that we have is we don't want any low frequency energy aliasing to other. Sorry, we don't want any high frequencies aliasing into low frequencies. And so if we don't have any energy in the low frequency spectrum here, and this is a spectral picture, then we're going to avoid that problem. Okay, so the way we actually want to do it is we want to do this irregular sampling here. All right, we want to basically just take random samples. And that's going to give us the best overall things. We're not going to have any of this sort of edge effects we do when we do regular sampling. Okay? How do we actually want to construct this thing? One way to do it is completely random sampling. We just throw darts all the time. And if you throw darts all the time, then you will get a frequency spectrum that is flat. That's white noise. Okay? It means there's equal energy at all pieces of the image. Okay? What we really want to do is we want to kind of like get rid of some of the low frequency noise here. And so instead we're going to do a different kind of sampling, and it's called blue noise. Okay? Blue noise is where the sampling is band limited. We're only going to have frequency components that are higher than a certain amount. Okay? And the way we're going to do that is we're just going to throw darts. But if we throw a dart and it lands too close to another dart, we're going to take away the dart we just threw. Okay? So another way you can do this is we could do Poisson sampling on this table if I took like a whole bunch of pennies and I put them on the table. And I just dropped pennies, and anytime a penny overlapped another penny, we'd take it off. Okay? So that's basically what you're looking at here. You're throwing a dart that's a disk. And if the disk overlaps any other disks, you pull it off. And then you just keep throwing darts. So one of the interesting recent work that's been done in SIGGRAPH is traditionally this has been a process that's been very serial. You throw a dart, you check it. You throw a dart, you check it. How do you do this in parallel? So there's been some recent work in the last couple of years where they looked at generating blue noise in a more parallel-friendly fashion, which was pretty cool stuff. Okay, so the really neat thing here is that this is actually what our eyes do, and that's why this is a good sampling pattern. This is somebody that took a rhesus monkey and cut its eye open and looked at the photoreceptors in the eye. Right? This is the sampling pattern in a rhesus monkey's eye. This is also what our eyes do. Okay? You'll notice this is a pretty darn good Poisson disk kind of distribution here. Okay? Then they took the Fourier transform of this particular sampling pattern. You see that it's got a DC component here, and it's got a very dark region in here. It doesn't have the sort of low frequency energy, and that's exactly what we're trying to avoid. So our eyes sample in this way. Okay, they sample in sort of this Poisson disk sort of way. And that's why it's a good idea that our graphics also does this, because it's going to create some sort of similar result.
So did those white dots are about a cone? Is that
right? Let's see. Those are cones. Okay, so this is where cones are. Rods are dense. Rods are at the fovea of your eye. Is that right? Okay, I'm seeing some nods over here. So basically we have rods and cones. So the fovea of your eye is, there's this one little region of your eye, okay, little tiny region that is really good at actually seeing stuff. Everything else is really pretty cruddy vision, right? It's very, like, I can stand here and I know I can see this clock here, but I can't read that clock if I'm looking at you guys, right? I can't possibly tell what those numbers are. The only way I can actually get any sort of detail is by taking this little tiny region of my eye and looking at the clock. And what your eyes are really good at is they sort of move very, 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 very quickly, and they sort of go over a big region. And when you read, your fovea is moving crazily. And it's important that your eyes do this. But the things that are, so the fovea is done by the rods, which are right at this little tiny region at the back of your eye. Everything else is cones. These are cones. So the fovea is densely sampled. The cones are much more sparsely sampled, but that's what we're actually looking at here.
So to generate the Fourier transform image, are you just taking the positions of each point and using it as the input to the...
Yeah, this is basically, they're point samples, right? So there's energy at each of these points. That is the frequency domain representation of this energy. Okay, optical Fourier transform. All right. Generating Poisson disk patterns is definitely an expensive thing. So how do we sort of fake that? Like, that's the right thing to do, but it's expensive to have a Poisson disk pattern. So here's what we can do. We can say, well, we don't want to take, we can do this. We can't test for Poisson disk when we're actually generating patterns. So what we're going to do is we're going to take a pixel, we're going to divide it up into 16 parts, and then we're just going to take a piece, we're going to take one sample in each part. Okay, so it's not really Poisson disk. If you look at this, you'll see there's some samples that are very, very close together. That we have this grid here. Okay, and it ends up taking a sample right there and a sample right there, and they're really close together. And we don't like that. Okay, but we're going to be able to live with it. If you look at the Fourier transform over there, you notice it's not quite as tight as some of the other ones. Like, you have some more bleeding into the low frequency energy. Okay. That being said, it's still a pretty good distribution, and so this is Smooth Vision is an ATI thing that did this. So I haven't seen the vendors really, go nuts about like, oh, we're taking these cool sampling patterns. Sort of at the beginning of this decade, they were really interested in having better and better sample patterns. Today, I think a lot of them just brute force it. They do full screen anti-aliasing and go nuts with it. But if you're Pixar, then you're really interested in doing like really good stratified sampling here, or really good Poisson disk sampling, so that you can get very high quality reconstructed images. All right, that's all I got on anti-aliasing. Anybody have any questions on that?
Okay, so from a practical matter, if we assume the object order OpenGL pipeline, that sort of thing, I'm having a hard time conceptually bolting together my view of the object order pipeline and sampling. Right. So if we're going to the approach where we render to a screen that's 2x resolution, that makes sense, right?
Okay.
That's brain dead easy to do. These other approaches with funny sampling and that sort of thing, how is that actually implemented?
Okay, so you got a couple choices. You got several choices. One is you just render the whole thing to a bigger frame buffer with one sample per pixel, period. That's what full screen anti-aliasing does. So then after you're done with the whole frame, you say, okay, these 4 points actually go to 1 pixel, so we're going to take those 4 points, squish them together, just average them all, and then send them out. Okay, so if you do multi-sampling, you kind of do the same thing. It's a question of resolving every time you draw a new sample and you need to composite it into the frame buffer, and compositing is the next thing that I'm going to say, there are rules for how you do that. So you get a new sample that comes in, what do you store the real questions you have to ask yourself are, what do you store per pixel and what do you store per fragment? Okay? So one thing is that you can store like a coverage mask per pixel. Okay? And each fragment says which pieces of the coverage mask it does. And then you can store a depth per coverage per sample. Sorry, depth per sample. And then you can composite in all these new fragments as they're rolling through. So you can do that along the way. So you can either do it sort of at the end of the process or along the way. The ideal thing to do is to keep all the fragments around until you're done with the whole scene and then smash them together at the end. And usually that means sorting them all and then rendering them back to front.
Okay. I understand that the missing link seems to be how do you tickle the rasterizer so that it generates these fragments at these unusual locations?
Okay, so depends on the rasterizer, but you have a sample point. The point can be anywhere. You basically evaluate 3 edge equations and you tell whether it's inside or not. It's easier to do it obviously on a regular grid, but as you rasterize, you can use any point you want to do the insidedness test.
Again, on kind of the practical side, when you're doing the Poisson blue noise thing and sampling, like how many samples usually per pixel would you want? Because you want to guarantee that kind of like you're at least taking some samples, like there's no white noise in between pixels so that nothing gets sampled.
Yeah.
But you don't want it too big either so that you're wasting a lot of time doing lots of samples that you don't need to. So where's kind of the golden area?
Sure, I'd say it's probably maybe more than 10, less than 100. Okay, that's just a rough guess. So I think you can see improvements in visual quality even in games as you're going from 1 to 2 to 4 to 8 supersampling. Okay, some people will turn on 8 because it looks pretty good. So when you're Pixar and you care even more, then you're probably willing to go beyond that. But you're also willing to not only have more samples, you're willing to do more interesting things with them. Instead of doing a regular grid, you're willing to do this stratified sampling or some sort of Poisson disk to make the sampling pattern better. This question, yeah.
You pre-calculate a full frame of blue noise and just use that over and over again?
You could, but that's. I think that's a good question. I think the issue there is, that's just a lot of storage and a lot of things. If you have to go fetch your location as opposed to being able to build it into the rasterizer, that's kind of an expensive thing to be able to do. Again, something maybe you could do in software, right? But if you're building a hardware rasterizer, it's pretty much locked down to doing certain patterns.
I think if you had like a very uniform like pattern texture or something, your eye might be able to catch like visual things there, like patterns inside the sampling if it's not totally random like that.
And we're really good at seeing artifacts. So, if you're taking an image processing class, hopefully they cover this stuff and they look at sampling and, look at these sort of noise spectrums and show what the artifacts are going to be. Okay. So, this was, I showed 1984, all these great papers, 1982, all these great papers came out of Pixar, and so one of them was this Road to Point Reyes video, so this is in Marin County. And let's see, so the big thing they did in this particular paper is they looked at algebra for being able to composite things together that had transparency. Okay, so if you actually look at these, it says that, I can't even read that word, that's plant over something road over something else, right? Hillside. It's hillside? Okay, you're doing better than I am. You're squinting more. Okay, hillside equals. And so they're saying we've got these different images or these different fragments. How do we put them together to make a single pixel? How do we take a bunch of fragments and put them together to make one pixel? Okay, so what we just talked about was this idea of, okay, where do we actually get the fragments from? And then we're done. We have this big list of fragments. We need to squish them together. How do we squish them together? So that's sort of what we mean by compositing. And one of the big ideas in compositing is this idea of alpha. All right, so every fragment has not only a color, okay, red, green, and blue, but it also has alpha. And you can think of alpha as a couple different things. One of them is how transparent the object is, okay? And two of them is how much of the pixel is covered. Okay, so you could say, well, I got something that's full blue, but it only covers half the pixel, so we're just going to call it alpha equals 0.5. And you can build a rendering system around either one of these. And if you're thinking about subsamples, then transparency makes sense, but not pixel coverage. Like, these are two different uses for alpha that both make sense, that are both useful to think about, but Jim Blinn had a list recently of his top 10 problems, and this is kind of one of them. How do you reconcile these two things? Because alpha is just kind of a big hack is really what it is. Okay, so the algebra that, 1984, was by Tom Porter and Tom Duff, and so they had this algebra for how to composite digital images together, right? You have two different fragments. How do you put them together? And so they had a language for how to do this, and they showed sort of, okay, we've got two fragments, and how do they combine, and this is sort of over, and how we want to do it, and so there was a lot of muckety-muck math to make this work. The most important one for our purposes is the over operator. Okay, so what we're saying is we have a source pixel, a fragment that's coming in, and we have a pixel that already has a color that's there. Okay, so this is sort of the destination. And we're saying if that's the case, then, and the source pixel has a particular alpha associated with it, then this is the equation that will tell us the final color of the pixel. All right? So you take as much here, so if this is an opaque fragment, okay, then you just take the source fragment color, right? That totally nukes out whatever was there. If you bring in something new that's opaque, it's going to cover up everything that was behind it. Okay? If you bring in something that's completely transparent, like Saran wrap, okay, then you're going to end up with the full color that was behind it. And between those two things, you're going to linearly interpolate. Okay? So it's pretty simple. The idea here is we don't, in hardware, have the ability to store all the fragments. So what we're going to do is every time a new fragment comes in, we're going to composite it into the frame buffer and only keep what's in the frame buffer. The nice part is that'll hopefully give us the right answer in the frame buffer. But there's a little bit of a problem. That's the problem. Okay. The problem here is that the over operator is not commutative. Okay? You can't take these fragments in an arbitrary order, that A over B, then over C is not the same as A over B over C. Okay? It is not a commutative operator. Or it's not, A over B is not the same as B over A. So the equation works correctly if you start with the things that are farthest away from the camera and you move toward the camera. The math works out that way. If you don't get things in that order, and you can't promise that things are in that order, then you're going to get the wrong, things will look incorrect. So we can do this by simplifying over to make it commutative, but then the visual impact of that is not so good. So generally, okay. So what that means is, as the programmer, you either have to sort things so that they render back to front, okay, or you're going to suffer the effects of not being able to do this correctly. So one of the big things that graphics hardware would really like to be able to do is what they call order-independent transparency. Okay? They don't want you as the programmer to have to sort things back to front. Instead, what they really want is to be able to throw fragments at you in any order. Nobody's really solved this problem yet either, or not in hardware, because what it requires is you have to keep all the fragments around and then sort them back to front. Nobody really wants to keep all those fragments around. So again, this is something Larrabee would like to be able to do well, to have to use software to be able to do this, to have an A buffer and to be able to do the resolution. So opaque objects, so the way people generally do this, they render opaque objects normally. For transparent objects, what they do is turn on Z-compare, so it'll throw away all the transparent objects behind the opaque objects, and then turn off the update of the Z-buffer, so as I'm drawing new transparent objects in front of my opaque object, I don't update the frame buffer. And then you want to go back to front. And then you can at least use your Z-buffer while you're doing this compositing sort of operation. Okay. One thing I will mention here, and I'm not going to go through the math here or anything, is how you actually represent alpha. Okay? If your color... Okay, what do you actually put in your... Okay, you have red, green, blue, and alpha. And your color is RGB with some sort of alpha. Not going to go through this at all just because we don't have time. But what you actually want to store in here is alpha times R, alpha times G, alpha times B. And then alpha right there. Okay? Not going to go through why. It turns out it's better computationally and ends up being much cleaner math when you're doing composite operations. So Albie Ray Smith has a very nice article on this if you want to read more.
Is it a numerical accuracy issue?
No, it's just there ends up being, the math looks cleaner if you actually look at the equations, and there's fewer operations to do. The other issue, in terms of cleanliness in my notes here, that that if you do non-premultiplied alpha, then the formulation for the first composite is not the same as the second, is not the same as the third, and so on. Okay, so let's say we throw in a whole bunch of fragments and we don't have them in order. Okay, we have this scene we want to render, and we really want to get order independent transparency right. Okay, and we're willing to go to more effort to be able to do it. How do we essentially do this sort in graphics hardware if we don't send in sorted primitives? If we're not sending them in front to back, is there any way we can get this right? Okay, so the answer is Cass Everett is, I think, still at NVIDIA, but did this really cool work called depth peeling. And so here's the way we're going to do it. Okay, what this requires is that if we have n deep things, right, so we render n different transparent surfaces, we have to do n multi-passes. We have to render the whole scene once, get the answer when we render it a second time and a third time. Okay, this is a multi-pass algorithm. I'll come back to the other one. Okay, where you render the whole scene to the color buffer, and then every future scene you render it in and you blend it with the color buffer. So any modern game today takes many passes to go through. Okay, they come in and maybe you have a pass where you compute shadows, and then the next pass you actually use the shadows. So games today take many passes to go through to build up their final image. So anyway, so this is a very important thing in a GL pipeline today. So one of the cool things was that Mark Piercy showed, I think this was in 2001 also, you can completely support the entire RenderMan standard in OpenGL if you have floating point fragments, which they didn't have at the time, and dependent textures, and multipass. So these three things put together meant that you could do even something as complicated as RenderMan in OpenGL, which was really pretty cool. It took thousands and thousands of passes, but it was possible. Anyway, so here's the way we're going to do this. We render the whole scene, all the opaque surfaces, and put the depth buffer for that in A. Okay, so we have depth buffer A and depth buffer B. We have to keep around two different depth buffers. So first we render all the opaque surfaces, depth is in A. Okay, then what we do is we try to render the farthest away surface. All right, and we take the farthest away surface that's closer than A. Okay, so we compare against A and we say, okay, are you in front of A? Yes, you are. Are you the farthest thing we've seen so far? Yes, you are. Okay, so what that's going to do is if I'm A here, it'll end up rendering the transparent surface that is as far back as possible. Then we store that depth in B. So we're always comparing to both A and B. Am I in front of A and behind B? Okay, so that's going to help me move all the way back and take the things that are closest to me. Okay, so then I render sort of this peel, okay, this peel out of the transparent surfaces. Then what I do is I step up and swap my frame buffers so that, or swap my depth buffers so that now my depth buffer is, I was that farthest peel. Now I render the next peel. Then when I'm done, I step up again. And so that lets me render back to front at the cost of n passes. Okay, so this algorithm works. You're going to get the right answer out of it. It's just a very expensive way to be able to do it. Well, every step you're
So you don't know what order they're coming in.
You don't know, but you're rendering the entire scene and only keeping the farthest back thing.
Okay.
Does that make sense?
Yeah.
Okay. So, first we render me and I'm the opaque thing in the back. Okay, and then we got two things here. We render it and I'm taking the thing that's closest to me that's farther back. So I'm going to only render this in that particular pass. Okay, then I step up and that's my Z buffer now, and now I render and this is the next pass. Okay, so as we move forward, we're going to do one per pass because my depth buffer just keeps marching forward.
What if you saw the one that was closer forward first and you rendered that?
Doesn't matter because I see that. I might render that first, but then later on in that pass, I'll see the thing that's behind it and I'll throw that out. So I'm basically setting my depth buffer to, instead of only taking the closest thing, I'm going to say take the farthest thing that's still in front of this frame buffer.
So you end up throwing out some work that you...
Oh yeah, you're rendering the entire scene n times. And just all you're going to keep out of every one is the next peel. Okay, so it works. It's expensive. Okay. Cool. All right, we're going to try to get through this all. Depth buffer. Okay, so first, we don't even need a depth buffer. All right, John Warnock, what did he go on to do? What's he famous for?
The Utah Engineering Building.
Okay, where did he get all the money to give the Utah Engineering Building? Okay, so he founded Adobe. I actually ordered his thesis because I thought this was a cool thing. It's 19 pages, double-spaced, typewritten, 19-page PhD thesis. The guy's a legend. Anyway, so here's the way we're going to do this. Warnock's algorithm lets you draw something and properly resolve depth without needing a depth buffer, which is pretty cool. So there's just a bunch of rules here. We're saying, all right, we're going to take a particular region of the screen, all right, and we're going to render everything against it. And so the first rule is, if my polygon doesn't intersect, okay, then I keep the background color of whatever was there. If it contains or it's intersecting, okay, the region that I'm doing, then I keep the background of whatever it doesn't cover, and I add the background to, and I add the new thing in front of whatever was there before. Okay? If I draw it and I'm clipping this region against this polygon, then I just recolor my whole region according to that particular polygon. And if I end up with something that doesn't fit into any of these categories, then I take my region and I cut it up into pieces, and then I recurse on those regions. And eventually I might recurse down to a single pixel. Okay? And it's a very expensive thing because for every region I'm sending every piece of geometry through it, so it's expensive, but I don't need a depth buffer. It's always going to be able to do the right thing there, which is pretty cool. So, 19 pages, including title page and acknowledgments. Okay. So I want to talk about 3 different technologies here. This was a talk in 2000 at the hardware workshop that ATI talked about their Hyper-Z technologies. These are all things that are smart things to do with a depth buffer. The reason this slide's up here is I just love to be in an industry where they label their products things like Evil Commando. Right? That's just fantastic. Can you read that? What does it say? It just says the name of the company, pretty much. Oh, that's boring. Nothing about an evil commando. No. Nothing about commandos who aren't evil. Okay, that's too bad. I just think that's a fantastic picture. Okay, so this is really cool. Okay, this idea of hierarchical Z. So one of the big ideas that we talked about is what we're really trying to do is reduce the memory bandwidth that we'd like to be able to use with our depth buffer. Okay, with any buffer. We're trying to reduce memory bandwidth as much as possible. It's too expensive for us to store an entire depth buffer on a chip. Okay, that's a lot of data. So instead what we're going to do is we're going to store a lower precision depth buffer. All right? And instead of having one depth value per pixel, we're going to have one depth value per tile. Remember we talked about why tiles were good. Tiles are great for rasterization. Okay, we want to rasterize in tiles. Tiles let us do things, get better locality out of our texture cache. Tiles are good. So maybe our tile is 8 by 8 pixels. Okay, and what we're going to store is for every tile what the maximum Z value is for that tile and what the minimum Z value is for the tile. Okay? Then when we start rasterizing something, okay, we check against these 2 things. Okay? And both of these things are useful in rasterization. Okay? Why is max Z useful? Actually, that's the hard one. Why is minimum... let's see, what do we want? Okay, why is maximum Z useful? I go in, I'm a polygon, I'm rendering. I go in and I say, I am all in this tile here, and this tile has a max Z associated with it. Okay, why is that useful? Okay, so I'm the polygon. What do I check? I go look at the max Z, and what do I say?
Am I further away than the max Z?
And then I say, am I further away than the max Z? And if the answer is yes, what do I do?
Go on to the next polygon.
Yeah, I stop, right? If you know you're rendering something, and it's farther away than the max Z of that particular polygon, you just stop, right? You can kill yourself. Okay? And then you never have to go to the depth buffer. Okay? You don't get rasterized, you don't get textured, you don't go through the fragment processor. You know that you're farther away than whatever's already there, so you throw yourself away. So that's great. Why is the minimum Z useful? Because
you're in front of everything there.
Yes? And what does that mean you can do that you couldn't do if you didn't know that information?
You don't have to do any Z compares.
Okay, so then if you're in front of everything, then you say, all right, I'm going to get rasterized, and I'm never going to have to check the depth buffer. Okay, don't even have to go check. I know that I'm going to be in front. So that's pretty sweet too. Okay, so everybody uses this. All the cool kids are using this technique today. Okay, they keep both a max Z for the tile and min Z for the tile. They just have to check something on chip. Bam, we're done. Great, that's really cool. All right, so that's one of the things.
If you're in between, then you have to do the Z check.
Yes. Right? And so the nice part is if this thing doesn't work for whatever reason, you just go back to regular rendering. But this saves a lot of bandwidth. Okay. Another thing that they try to do is Z compression. So they're saying, all right, I've got a tile of Z values here. Okay? I need to send those back out to the memory. I don't want to have to send a full bandwidth out of all that stuff. Okay? Instead, I would like to be able to compress it. And one important thing about this compression is it needs to be lossless compression. Okay? You can't do lossy compression with a Z. You can't do JPEG compression with it. You need to actually compress it well. So if we have, say, an 8x8 block of Z values, how do we represent that and try to squish it a little bit? And so this is actually the stuff that the ATI said in their presentation, and they were really wishy-washy about it. And it's all these buzzwords. I think you can get this out of their patents if you really need to. What Tomas has indicated is if we just look at one column, this is the way we do it. So we're just like compressing this particular column of Z values. What you're going to do is you're going to figure out slopes here between sort of what the delta is between here and here. Okay, so you can build this in special purpose hardware. And you do that twice. So you do differential slopes there. And the expectation is that there might be slopes between, you might have a nice smooth Z value differential here, in which case these slopes are all going to be, possibly big or small numbers. But the second derivative is probably going to be pretty small. Right? If it's something flat, the second derivative is going to be 0. All right? So we're going to try to compress that. All we're storing is D0 and S1, and hopefully those deltas are small. Okay? For linear functions, they should be 0. And so when we reconstruct this, when we reconstruct this, we can say, all right, those deltas, we're just going to say we're going to use 2 bits for those. One is 0, one is +1, one is -1, and then we can have escape code to say, all right, if we have a big delta, then we'll just represent that flat out. Okay? And so basically, for every Z tile, you try to compress it if you can, and then you just send back the compressed one if you can. Some of them you can't do very well, and if you can't do it very well, then you just use this instead, and you use an uncompressed tile. So, but if you compress, you're potentially, cutting out, going down from 100% to 13%, and that's really good. So, this works on. So this is interesting for both color buffer and depth buffer, and this is a real key technique in modern GPUs as they try to reduce bandwidth. How do we do lossless compression of tiles of our depth buffer and tiles of our color buffer? Okay, and let me just check where we are. Okay, so the final thing that I want to cover today is this issue of fast Z clear. So this was something Doom did. It was one of the first games to actually do this. So what ATI said in this particular talk is that what a real-time application does is they clear the Z buffer, they don't clear the color buffer, and they draw every pixel once. So if they clear the Z buffer, what they're doing is they're taking the Z buffer and moving it back to the farthest place. And if you draw every pixel once, then you're guaranteed that you're going to, since every pixel is now associated with the farthest away Z value, you know that any pixel you draw is going to be in front of the one that was already there. So you don't have to clear the color buffer, okay, because you know you're going to overdraw every single pixel in the color buffer. So that's good. So that's going to save you. So what they wanted to do was avoid the clear and avoid the first read. So this works very nicely with compressed Z buffer and compressed color buffer. So every block in memory, meaning every tile, is marked either compressed or uncompressed or cleared. And so if you want to clear the depth buffer, for instance, then you mark it as either compressed or uncompressed, or you mark it as cleared. And if it's cleared, then you know that it's the farthest away thing. And so when you compare against hierarchical Z, okay, in the hierarchical Z step, you know that it's cleared and you know that it's as far away as possible. So when you start it out, it just it lets you mark an entire tile of something at the same time instead of having to mark every individual thing in there. So that's kind of nice too, and it works very nicely with the hierarchical schemes. Okay, the last thing I have to cover that I'm not going to do today is we'll go through some issues with monitors, which are kind of cool as well. And we'll sort of combine that into the next lecture. I'll see you guys on Thursday.